In this video, we're going to take a look at some of the energetics of bonding. So at the end of this video, and after doing some practice, you should be able to predict the relative lattice energies for ionic solids based on their charge and ionic size. And you should also be able to predict the enthalpy of a reaction based on the relative bond energies and lengths in the reactants and products. So first, we're going to start out looking at ionic compounds. As we know, ionic compounds are alternating lattices of cations and anions, and they're held together through an electrostatic attraction. And the atoms are arranged such that interaction is maximized, and that results in the most stable structure. And we use the term lattice energy to describe the strength of that ionic interaction. So the lattice energy is actually, by definition, the energy associated with the individual ions in the gas phase. So here we're showing sodium and chlorine as gases coming together to form solid sodium chloride. This process is always going to be exothermic. It's always more stable for those ions to come together. And that enthalpy associated with this process is what we call the lattice energy. It turns out that we can't measure this lattice energy directly. We have to calculate it based on knowledge of other processes. And if you're interested in learning more about this, you can look into the Born-Haber cycle. More importantly for our purposes is the qualitative effects on the lattice energy of the charge and the distance between the ions. So the interaction of two charged particles is described by this Coulomb potential, where we have basically this product of the charges divided by some constants and the distance between those charges. And based on this, we find that the energy, particularly the potential energy, is going to be proportional to the product of the charges, and it's also going to be inversely proportional to the distance between them. So first, let's look at the ion charges. So if you have a larger charge, that means the ions are going to be more strongly attracted together, and therefore we're going to have a higher magnitude of the lattice energy. And so here's an example where we have sodium fluoride, which has a +1 charge on the sodium and a -1 charge on the fluorine. And that has a lattice energy of -904 kilojoules per mole. The compound consisting of calcium with a 2+ charge and oxygen with a 2- charge has a lattice energy that's not quite, but nearly 4 times that amount. And so generally this is the most important factor. There is a slight difference in the bonds here, but the charge is really what determines the relative energy. In this case, because the energy is negative, the lower energy is going to be the more negative value. That's going to correspond to the stronger bond. It's going to be harder to separate calcium and oxygen than it would be to separate sodium and fluorine. We can also look at the trend as a function of the ion size. And this comes from the fact that the attraction between charged particles is going to affect the energy as a function of 1/r. So as this r gets bigger, as the atoms get further apart, the energy is going to go down. And these are the same trends, by the way, that we looked at when we talked about ionic compounds dissolving in water. Now we're just looking at the ionic compound in isolation. And the lattice energies, again, correlate with this distance. So the bigger negative value is going to be the lowest energy. That corresponds to lithium chloride. That's going to be the most stable compound. It's going to be the hardest to pull apart. And so as we go down the period, we see that the bond length gets bigger. That also directly correlates to the size of the cation, which is getting bigger. And in this case, our anion is staying constant. So the take-home message here is that in ionic compounds, the energy is determined by the charge and the size of the ions. And if we have a lower energy, that's going to result in a stronger bond. It's going to result in higher ionic attractions. Now let's move on and think about some molecular compounds. So in molecular compounds, we're always thinking about two atoms which are sharing electrons. And so that results in a lowering of the energy when those atoms are allowed to interact. And that gives us a more stable structure. And so when we're looking at molecular compounds, we need to remember that it always takes energy to break bonds. That process is endothermic. It also always releases energy when you form bonds. That process is exothermic. So in a chemical reaction, we're generally looking at the sum of two processes. We're looking at bonds breaking and then also looking at bonds forming. And the difference between those gives us our overall energy change of the reaction. So in this case, where the breaking of the bonds requires less energy than the forming of new bonds, we have an overall change, which is exothermic. If it were the opposite, it would be endothermic. So we can use these bond energies to estimate the enthalpy of the full reaction. The exact bond energy would depend on the surrounding atoms. It depends on the exact compound we're dealing with. But we can use an average bond energy to get an estimate. And that average bond energy is generally the energy associated with many different compounds consisting of similar bonds. And so this is going to work best when all reactants or products are in the gas state. So we can calculate our delta H of the reaction as the sum of all the bonds broken minus the sum of all the bonds formed. Sometimes you will also see this written with a positive sign, but in that case, the enthalpy would be defined as a negative. So just be careful that it always takes energy to break bonds. This quantity should be positive. It always releases energy when you form bonds. So this second quantity should be negative. And these bond enthalpies are the kind of thing that you could look up in a table. So here's an example of such a table where basically we have the type of bond and the energy associated with that bond. So we can think about how this would apply to a reaction by looking at the case where methane interacts with chlorine gas to form methyl chloride and hydrochloric acid. So first we need to consider the bonds that are breaking. That would be the carbon-hydrogen bond in methane and the chlorine-chlorine bond here. And then we also need to consider the enthalpy of the bonds that are formed. And so the carbon-chlorine bond is one that's formed, and the hydrogen-chlorine bond is the other one that's formed in this process. And again, if we went back to the table, we could look up actual numerical values that went along with each of these cases. So a couple trends we can pick out from that bond energy data. So the first is that if you have more shared electrons between the atoms, you're going to end up with a stronger bond. And to make sense of this, we really need to compare similar types of bonds. So here we have an example with carbon-carbon. We have a triple bond where you're sharing 6 electrons. We have a double bond where 4 electrons are shared, and a single bond where 2 electrons are shared. And you can see that the energy decreases as we go from 3 to 2 to 1. Also, if you have a shorter bond, that's going to correspond to a stronger bond. For much the same reason that we saw in the ionic compounds, if the distance between the atoms gets smaller, that attraction is going to get stronger. And so this means that it's going to follow basically the periodic trends with atom size. So if we're going from bromine and fluorine to bromine and chlorine to bromine and bromine, one of these is getting larger, and so the bond is progressively getting weaker. This also leads us into thinking about the lengths of bonds. So bond lengths are basically just the distance between nuclei for bonded atoms. And again, this is going to depend on the surroundings of the molecule. This is going to depend on the exact compound that you're dealing with and the exact atoms involved, but we can discuss the idea of an average bond length where we're kind of comparing the average from many different compounds. Again, we see trends in our bond lengths in that longer bonds tend to be weaker, and the bond is going to get shorter as you go from left to right across the periodic table because the atoms are getting smaller, and it's going to increase as you go down a column because the atoms are getting bigger. And again, if we have multiple bonds, those are going to be shorter than single bonds, and generally a shorter bond is going to be equal to a stronger bond. So you can keep that in mind. Again, these bond lengths are the types of things we can look up in tables if you need to know specific values. Before we end this video, it would be a good time to take a minute and do a practice problem. So I would recommend that you pause the video at this point and make an attempt at calculating the enthalpy for this reaction based on the bond energies that are given in the table on this side of the slide. Assuming you've gone ahead and taken a minute to pause, you can keep watching for the solution. So in this process, the bonds that we'll be breaking are between a carbon and an oxygen and between a hydrogen and a chlorine. So the bonds broken are these two, and you can see that the energies that correspond to those types of bonds. We're also forming bonds. We're forming a carbon-chlorine bond and an oxygen-hydrogen bond. And so we can identify the energy associated with those as well. If we go ahead and look at the enthalpy of the reaction that we want to calculate, we would take the enthalpy of the bonds broken and subtract the enthalpy of the bonds formed. And so if we plug in the values from the table, we should get this, and a total of negative 12 kilojoules per mole. Now, in a more complicated reaction, it may be difficult to identify exactly which bonds are being broken and formed, but the good thing is that it doesn't matter. Because enthalpy is a state function, it doesn't matter how we get from reactants to products. It just matters that we get there. So you could actually consider all the bonds breaking in the reactants and all the bonds forming in the products. And you can test it out and see that you should get exactly the same answer if you do it that way. So that's all for this video. Hope to see you again soon.